it is a section 2.4, zeros of polynomials. A polynomial of degree n has a form as given in this equation. In this section, we'll try to find the zeros of such polynomials. Before that, let's consider some theory on polynomials. The first one is fundamental theorem of algebra. Every non-constant polynomial has at least one root, possibly in the complex field. That means that every non-constant polynomial should have a linear factor. If we apply this theorem recursively, then every non-constant polynomial must be factored into linear factors. So it must be a product of linear factors. So this is the conclusion of that theorem. A polynomial of degree n has exactly n roots in the complex plane. Once it is, the number of roots must be counted along with its multiplicity. That means here there are unique complex constants x1 to xr which are zeros, and unique integers m1 to mk, they are multiplicity, such that the polynomial degree n can be written in this way. So it is a product of linear factors. And of course, the addition of multiplicity must be n. Localization of roots. When we try to get zeros by using iterative method, like Newton's method, the initial value must be given. And if we know where the roots are, then we can get, we can choose the initialization much more effectively, and we can get the solution more easily. So that's the reason localization of roots are considered from old days. All roots of polynomial p lie in the open disk centered at the origin and of radius rho. The rho is defined in this way. The maximum is chosen from a1 to an-1 and divided by an absolute value, and 1 is added. So here you can easily see the disk of radius rho in the complex plane. Then here all roots are inside this disk. And now here, uniqueness of polynomials. If two polynomials of degree n are the same at r distinct points, here x1 to xr, and two polynomials are the same, then two polynomials are identical. Two are same for all points means they are identical. Particularly when we choose n plus 1 points, so r is larger than n. But in the special cases, n plus 1 distinct points, and once two polynomials are the same at n plus 1 distinct points, then they are identical. That means that by using n plus 1 points, a polynomial can be determined uniquely. And so that's the conclusion of the theory. Okay, now here we'll consider Horner's method. The method is known as nested multiplication and also known as synthetic division. You learned this one from high school. And Horner's method can be used to evaluate polynomial values very effectively. It requires only n multiplications and n additions to evaluate an arbitrary nth degree polynomial. It's quite efficient. Here is the algorithm. Here we'll try to evaluate p of x at x0. Now, the algorithm starts with the remainder theorem, and we can rewrite the polynomial in this form. That is remainder theorem. R is a constant because the divisor is linear, and Qx is quotient. And if we plug here x is x0, then this will disappear. So R must be p of x0. So we replace R with p of x0. So we have here p of x equal x minus x0 times q of x plus p of x0. Now we write the quotient q of x symbolically in this way. Now we plug this one to this equation and expand, and we try to set equal the coefficients of like powers of x. And then we have such equations. So the first one is came from the coefficients of xn, and that is from coefficients of xn minus 1. From both sides, you can get it. Okay. This one, if we try to put here, for example, plus x0 and bn plus 1, then it's the same form. Here, bn, an, x0, bn plus 1. bn minus 1 is a n minus 1 plus x0, bn. So here, indexes go down here. And of course, for that one, we try to define this one as b0. Then, now, all of this equation can be written this way. Of course, this must be 0, so that bn plus 1 is initialized to be 0, and then we try to compute the pk recursively in this way. And last one, b0 must be the function value. Okay, so we organize these identities into this synthetic division. You learned this one from high school. Now, we collect the coefficients of polynomial, and x0 is here, and an go down here to become bn, and multiplication is here, and addition, and multiplication, and put here an addition, and so on. So the last one must be b0, which is the same as p of x0. Let's see this example. We'll use Horner's algorithm to evaluate p of 3, where p of x is given this fourth order polynomial. We collect the coefficients 1, minus 4, 7, minus 5, 2. These are the coefficients, and now 3 is here, and in synthetic division, it go down here, multiplication, addition, multiplication is here, and addition, and multiplication is 12, and addition is 7, multiplication is 21, and addition is 19. That is p0 and p over 3. And here, that represents the quotient Q of x. So the polynomial can be written in this way. X minus 3, and these are for Q of x, 1, -1, 4, and 7 here. And that is the remainder, which is P over 3. Okay? Okay. For this synthetic division, we know there are only n multiplications and n additions required. So it's quite effective. Now, when we try to get zeros of a polynomial by using, for instance, Newton's method, then here in each iteration, you have to get the polynomial value, and also you have to get the derivative value. And here we'll consider a technique. We'll apply the Horner's method one more time to get the derivative value without finding or organizing polynomial derivative explicitly. Okay. Now, in order to get p prime x, we start from that equation here. Now we differentiate both sides. Then p prime x will be q of x plus now x minus x0 q prime x by using the product rule, and this will disappear. That is exactly here, this one. Now we need, because we don't know this one explicitly, but we need only p prime at x0. So if we plug here x0, then no matter what it is, it's a bounded number, and this is 0, so that will disappear. And p prime x is the same as q of x0. Now, as a byproduct of synthetic division, we already have here the q, and we have to get q at x0. Now, here x0 is 3, so that we may apply one more time with synthetic division. Okay, here, and evaluate p prime 3 for p of x considered in early example, the previous example. Now, we did up to this point, and we know that is q, and we have to have right now evaluate this q at 3. So here we apply one more time of the Horner's algorithm, and 3 is here, go down, multiplication is 3, and addition is 2, and multiplication with 3 is 6, and addition is 10. Now multiplication is 30, addition is 37, which is the same as q at 3. Now earlier we already know that there is p prime at 3. So we found the function value, the polynomial value, and its derivative value at the same point by using here twice of Horner's algorithm. Here now we'll try to implement the Horner's algorithm to evaluate p of 3 and p prime of 3 for the polynomial. Okay, that is Horner.m is a MATLAB code. Here we assume that the coefficients are given from A0. For some software, if you are using automatic, the built-in function to get coefficients from polynomial, then sometimes it's made from A0. So we assume the coefficients are here collected from A0. Then now this iteration, that's the major part of Horner's algorithm. Now that is D first. D, the final D will be your derivative value, and after finishing this iteration, the final P will be the polynomial value. Okay, so start with here coefficients and init the point x0, and you can get this one. If you follow the logic, then you can find it quite easily. It's working for exactly the twice of the Horner's algorithm. Okay. Now here we collect the coefficients now from A0 and x0 to 3 for the earlier, the polynomial used in earlier example. Then we call Horner.m this one, and then here print out. So here P of 3 is 19, P prime at 3 is 37. Is they are correct answers. Okay. Now here for the polynomial, we use the Newton's method and the Horner's method to implement a code and find an approximate 0 of P near 3. That means that start with 3 and we try to find around 3 or 0 of the polynomial. Okay, there's Newton Horner, and again coefficients are collected from A0, and here x0 must be 3, and here inside once polynomial value and its derivative value is made, then that is correction term, and correction term is added to update. So this portion is Newton's method. For evaluation of function value and polynomial value, we are using Horner's algorithm implemented earlier in this one here. That is Horner.m. that will be used. Then here now the coefficients, the initial value, and tolerance is 10 to the minus 12, and max is 1000. And after calling Newton-Horner, and we get the solution root and number of iteration and happened during this iteration. Okay, so the result is Newton-Horner and start with 3, and now final result is 2 in 7 iterations. So after 7 iterations, we get the answer. Here in this picture, now one solution, one root is 2, and another one is here. That is minus 0.27 something. Now start from 3, and we got that root. Okay, in 7 iteration. Of course, we are using Horner algorithm to evaluate the polynomial value and its derivative value. Okay, so it's quite efficient. Okay, that is end of part 1. We'll continue in the second part. Thank you.